Hello, we are members of ISET2 under the guidance of Dr. Christine Simurda. My name is Carolyn and I'm a rising junior from New Jersey.
My name is Joanne and I'm a rising junior from Washington. We are proud to present our research on monitoring wildfire-induced disruptions to vegetation health. Each year, wildfires across the United States inflict millions in damage to infrastructure, economies, and entire ecosystems. As wildfires become increasingly erratic in frequency and intensity, resources need to be allocated to monitor them. Thus, tracking vegetation changes over the duration of these fires is imperative to actively and effectively assess wildfire risk. This research endeavors to develop a comprehensive profile of vegetation disruption across a range of NASA satellites like ISAT-2, MODIS, and Landsat-8. We focus on two major wildfires in California, the 2018 Camp Fire and 2021 Dixie Fire.
We used the following questions to formulate our research hierarchy. First and foremost, we decided to look at vegetation health, and namely how it changed. So for that, we focused on the indicators of plant health before and after the fires. And we also looked at how vegetation indices such as NDVI and EVI can track both plant damage and recovery. Next, we looked at vegetation index and structure, namely, which plant species could be classified as the most and the least resilient, or how they may react differently to fires. And finally, we looked at the large-scale forest temporal data, namely, how physical changes to the impacted regions can be verified using remote sensing imagery. Through analyzing all these visual and spectral data points, we sought to verify the hypothesis as listed on the slide. The implications of our research are especially important in areas characterized by dry or volatile climates and with few existing resources to surveil wildfire conditions. The following table lists out preliminary background research on each of the fires we studied. What's important to note is that the Dixie and Camp Fires occurred roughly in the same area, although not in the same time frame. However, they were similarly devastating in the scale and long-term damage they caused.
The first fire we will be reviewing is the 2018 Camp Fire. The exact coordinates can be seen on the slide along with images of the canopy height and ground elevation levels collected from the ISAT-2 open altimetry platform.
This is a forest profile of the area impacted by the Camp Fire. According to our ML tree species classification map, this region can be characterized as a largely homogeneous conifer forest, with the fir, pine, and aspen species being the primary ones sampled during classification and then studied during research.
The next fire is the 2021 Dixie Fire. Again, the exact coordinates and ISAT-2 canopy height images can be seen on the slide.
The Dixie Fire occurred primarily in the Plumas National Forest, and the majority of tree species impacted include, again, the fir, pine, and aspen families. Using the same predictive algorithm to map tree species classification onto the region, we were able to identify the primary species present in specific parts of the impacted region.
Next, we'll be going over the remote sensing instruments we used. Remote sensing is observing information of an area without physically making contact to the area. The table shown below describes the instruments we used, including the spatial, the spectral, and temporal resolutions. The Ice Cloud and Elevation Satellite, or ISAT-2, is a LiDAR altimeter used to evaluate the average tree height in the affected area. Next, the Moderate Resolution Imaging Spectroradiometer, or MODIS, is an instrument sampling the visible, near-infrared, and thermal infrared wavelength. Lastly, the Landsat-8 satellite is a visible and thermal sensor.
Throughout this research, we utilized data from the MODIS, Landsat-8, and ISAT-2 instruments. For MODIS, we looked at the products corresponding to vegetation health and surface temperature. Next, we also used data from Landsat-8, focusing on Level 2 data products, and created virtual rasters from specific band ratios for further vegetation analysis. And finally, from ISAT-2, we looked at ATL03 and ATL08 to measure the land and vegetation height. By using such a wide range of instruments, we aim to better compare indicators of plant health and therefore develop a more comprehensive profile for vegetation status pre- and post-wildfire.
For our methodology, we calculated 4 different vegetation indices: the Normalized Difference Vegetation Index, Enhanced Vegetation Index, Normalized Burn Ratio, and Vegetation Fractional Coverage. We then visualized band combinations that were used to review more vegetation indices.
The last point in our methodology trifecta was the use of supervised ML models, namely a CART, or classification and regression tree predictive algorithm, to map burn severity and tree species over the regions of interest. CART utilizes a decision tree where each fork is a split in a predictor variable and each end node contains a prediction for the outcome variable. In our case, the predictive variable were the feature collections we manually imported into the model as training data, and to sample areas for training, we cross-referenced maps of native vegetation in California provided by calscape.org. Meanwhile, our severity map was validated using real burn severity maps released by Earth Explorer or the USGS, as well as special MODIS burn products. and overlaying classification maps for burn severity and tree species between both wildfires denoted the aspen and pine families as being the most resilient of the vegetation studied, while areas dominated by more vulnerable vegetation, like the Douglas fir, were marked as high risk for succeeding wildfires. Figure 1 exhibits how we referenced an actual burn severity map during the model training process, ultimately yielding an R-squared value of 0.84 for our classification map. Figure 2 is an image of our training and validation feature collections, with the colored polygons representing our geometric imports. And finally, our JavaScript code is captured in Figure 3. Note that we coded the entire model through Google Earth Engine, which is an online code editor with an access to a breadth of satellite instrument data. Now, let's get into the specific analysis and results for each fire.
First, to establish the scope of the wildfire, the burned area on the top left shows where the fire burned, and the thermal anomalies map at the bottom shows areas where the temperature is uncharacteristically hot or cold, but in this case, hot. The burn severity classification was derived from the previous two maps and shows the severity of the burns from the campfire.
In addition to burn severity and burn area, we also analyzed several vegetation indices, including NDVI, EVI, and FPAR, or the fraction of photosynthetically active radiation. From these cumulative analyses, a few distinct patterns emerged. Overall, graphed changes in vegetation indices corroborate different Landsat visualizations made in QGIS. Simply put, what we observed graphically matched what we also saw visually. The following graphs all show clearly how NTVI, EVI, and FPAR values decreased sharply following the start of the campfire, so November 8th. And pivoting to the EVI short-term time series to the left, we see how EVI decreases by 0.10 just a week after the fire began. And while this observation may be attributed to seasonal changes in plant health, the disruptions to yearly cyclical EVI patterns evidence otherwise. As the EVI long-term time series shows, EVI does not drop as drastically nor as severely as it did first following the fire. In fact, it took an assessed recovery time of nearly 5 to 6 months for EVI values to even return to a stable pattern, with EVI yet to return to its pre-fire level.
As can be seen through the data collected from the ISAT-2 satellite, the canopy heights of the vegetation before the camp wildfire had an average of around 50 meters, while afterwards the canopy heights were around an average of 25 meters. The Landsat data shown below are the differences of the before and after data collected in the same area. The red part of the images show that the data had worsened conditions after the fire, while the green part of the images show improved conditions of the fire. The DNVR image indicates the burn areas of the fire, the DNDVI measures the vegetation health, the DVFC records vegetation cover, and the last image, DEVI, calculates vegetation greenness. Overall, the differences in the before and after image data are clearly identifiable in QGIS visualizations.
Next, we'll be going over our Dixie Fire analysis. Using a similar process as with the campfire, first we analyzed and mapped thermal anomalies onto our region of interest by referencing specific MODIS burn products. The burn severity classification map on the right actually mirrors the official MODIS data products nearly perfectly. Analysis conducted on the Dixie Fire had, by far, the most apparent impacts to vegetation, validated across indices and visualizations. As the NDVI visual time series shows, NDVI wanes in the triangular region during the course of the fire and continues to decrease until vegetation eventually regrows. Our graphical analysis for the Dixie Fire most prominently displays an abnormal drop in NDVI, EVI, and additional vegetation indices post-fire, with the turning point hitting at approximately July 7th in all of the graphs displayed below. Regardless, the data tells a very steady story. Right at the start of the fire, vegetation indices decreased drastically, which is indicative of how fire adversely affects vegetation health. And these vegetation indices anomalies are still compounding over time, even marginally decreasing 2+ years after Dixie ended. And from this, we were able to assess that the Dixie Fire had a recovery time of approximately 5 months, similar to the campfire, with long-term recovery still ongoing.
The ISAT-2 data shows that the average canopy height before and after the fire only decreased a little, but the amount of vegetation left decreased significantly. Like the Landsat data shown in the campfire comparisons, the red part of the images show that the data had worsened conditions after the fire, while the green part of the images show improved conditions of the fire. Overall, the changes in the vegetation are only slight and not drastically different. For future applications, we recommend 4 main points. First, to identify more areas that are prone to wildfires. Next, to collect long-term data and evaluate if plants adapt to wildfire conditions. Then, to broaden vegetation in samples by mapping more species affected by wildfires. And lastly, to replicate our methodology within another region.
We would like to extend our sincerest thanks to Dr. Christine Simurda, Margaret Baggio, and Selena Miller, as well as every incredible individual involved with NASA Seas.
We know we will bring the knowledge and skills gained here into our future academic and professional pursuits. And here are our citations.
Thank you for listening.